TAs need a vacation. There are 251 students in a class, and the TAs are so tired and so in need of a vacation that instead of handing back the midterms properly, the TAs randomly permute the midterms before handing them back. Let X be the number of students getting their own midterm back. What is the expected value of X? So our end goal in this problem is going to be to try and find the expected number of students who get their own midterm back even though they were all handed out randomly. So first, as a warm-up, compute the expectation using the definition of expected value, assuming there are just 3 students. Then, for the main problem, compute the expectation for 251 students using indicator random variables and linearity of expectation. So that's a lot of key terms we just saw there. We got definition of expected value, indicator random variables, and linearity of expectation. So let's fetch those definitions from the textbook. This is expected value, indicator random variables that come with this nice property, and linearity of expectation. With all of these key definitions in our toolbox, let's jump right into the warm-up. In the warm-up, we want to use the definition of expected value. So this definition is just a sum over the range of X. So the range of X is all possible values that X could take on. And then we need the probability that X is equal to any particular value in that range. And in our case, X is of course the number of students getting their own midterm back. So for this warm-up, we're only assuming there are just 3 students. So let's go ahead, pick our 3 students. Let's say we've got Bubbles, Blossom, and Buttercup. What are all the possible ways we could hand their midterms back? If we get lucky, maybe we get it right and we hand Bubbles her paper, Blossom her paper, Buttercup her paper. But of course, there are a bunch of other options. We could hand Bubbles back her paper, but then we swap up the last 2. We could hand Blossom and then Bubbles, and then Buttercup does get her own. And like this, we can enumerate all of the other possibilities. In total, since there are 3 girls, there are 3 factorial or 6 different possibilities. And notably, all 3 factorial, all 6 of these permutations are equally likely since we randomly divvied up the papers. Now for each one of these cases, we can kind of just read out and count what X is going to be for each case. In the first case, all 3 students get their paper back, so X is equal to 3. In the next case, only Bubbles got her paper back, so X is equal to 1. In the next case, only Buttercup got her paper back, so X is equal to 1. In the next case, it all got scrambled up, so none of them got their papers back, so X is equal to 0. And like this, we can go through the remaining possibilities, and we've enumerated the entire table. Now that we have all of this listed out, we have all the pieces we need to apply this formula. Reading off the table, we can see that the range of X goes from 0 to 3. So plugging that into the formula, the expected value of X is going to be equal to 0 times the probability that X is 0, plus 1 times the probability that X is 1, plus 2 times the probability that X is 2, plus 3 times the probability of X is 3. And you might have noticed you can skip over this term, but we'll see it doesn't matter either way, it gets canceled out. So for the first term, we have 0 times the probability that X is 0. Well, there are exactly 2 different cases out of the total of 6 cases where X is equal to 0. And since each of these cases are equally likely, the probability that X is 0 is 2 over 6. And like this, we can go through each of the terms. So we've got 1 times the probability that X is 1. Well, there's 1, 2, 3 different ways where X could be 1 out of the total of 6. So the probability that X is 1 is 3 over 6, plus 2 times the probability that X is 2. Well, there's no way that X is 2, so this is just 0. And we can see that this term does indeed cancel out. Plus 3 times the probability that X is 3. Well, there's 1 out of 6 ways that X is equal to 3. So now we've got all our terms in order. We can go ahead, do the math, simplify it, plug it into a calculator, do it in your head, and it all simplifies down to 1. Awesome. We can go ahead and check off the warm-up and jump right into the main part of the problem now, where we want to compute the expectation for 251 students using indicator random variables and linearity of expectation, where X is the number of students getting their own midterm back. Before we jump into all of this mumbo-jumbo notation, you might be wondering, why do we even have to deal with that? Why can't we just do the same exact thing we did with 3 students? With 3 students, we found that the expected value was equal to 1, and we did it by just applying the definition of expected value straight up. The reason we can't do that again is because in order to use this definition, we needed this term right here. We needed the probability that X was equal to any particular value. And this is actually, in general, hard to calculate. The reason we were able to do it with 3 students is that we just manually listed out all 3 factorial or 6 different options and read out these probabilities from the table. If we were to make a similar table for the 251 students, that table would have well over billions of rows, and there's no way we're going to be able to manually enumerate all of that. So that's not really feasible. So we have to go to our second strategy, which is using indicator random variables and linearity of expectation. Indicator random variables are just random variables that can only be equal to 1 or 0, depending on whether or not a certain event occurs or doesn't occur. Because they're defined this way, it actually turns out that the expected value of an indicator random variable for a certain event is always just going to be equal to the probability that that event occurs. Linearity of expectation, which you might also see written out in a different way like this, just means that the expected value of the sum is equal to the sum of the expected value. The only difference between these two is just notation, so either one is fine. The reason this duo is so helpful is because if you can find a way to represent the expected value of x as the expected value of a sum, you can break out that sum into each one of its expectations. And if each one of those random variables are actually indicator random variables, you can replace the expectations with probabilities. So if we want to use this duo, our new goal becomes trying to find a way to define x as a sum of indicator random variables. In other words, we want to find x in terms of a bunch of xi's summed together, where each one of those xi's can only be equal to either 1 or 0, depending on whether or not an event occurs. With this in mind, the only things we have left to really specify is how many xi's are we summing up, and what do they represent? When are they equal to 1, and when are they equal to 0? So go ahead, take a second and pause here and try and fill out these yellow boxes yourself. All right, and we're back. Hopefully you found that the most natural way to represent this is actually going up to 251 xi's. This way we have an xi, or an indicator random variable, for each student. That can be equal to 1 when they get their own midterm and 0 if they don't. Each of the xi's kind of acts as like a flag, and when we sum them all up, we count up the number of students that get their own midterm back. Now that we've set up our definitions, let's apply them in the formulas. We want to find the expected value of x, which by our definition is just equal to the expected value of the sum of all these xi's, and then by linearity of expectation, that's just equal to the sum of the expectation of each of the xi's. And since each one of these xi's are actually indicator random variables, we can replace the expectation of each xi with the probability that student I gets their own paper. So what is the probability that student I gets their own paper? This is just going to be a fraction where the denominator is the number of possible ways we could hand out all of the papers, and the numerator is the number of possible ways we could hand out all the papers where student I gets their own paper. So take a moment, pause here, and try and find the probability yourself. And we're back. So the denominator is going to be equal to 251 factorial. That's the ways that you could permute all of the papers. And the numerator is going to be 250 factorial. You can think of this as like fixing student I, they get their own paper, and we just need to find out how many ways to hand out the remaining 250 papers. This fraction simplifies really nicely to just 1 over 251. So let's substitute that in, and we just add 1 over 251 times, so that simplifies super nicely to just 1. Awesome, so we can check off the main part of the problem too. But before we leave, want to touch on some takeaways. The first takeaway is that the expected number of students who got their own paper back was actually completely independent of the number of students. So if x is the number of students getting their own midterm back out of n students total, we actually found that x is equal to 1 over n times n, which is always equal to 1, regardless of whether n is 3 or 251 or 8 billion. And this may not be super intuitive at first, but it does work out when you do the math. The second takeaway I want to give is just going over the strategies we just used today. First was applying the definition of expected value. But in order to apply this definition, we did need to know the probability that x was equal to any particular value. Sometimes this can be hard to find, so we have a second strategy where we combine indicator random variables with linearity of expectation. This can be really nice because if you define your indicator random variable nicely, this probability should be a lot easier to calculate than this probability. And that's all. Bye!